Neutron stars are the remnants of massive stars that have undergone supernova explosions. When a star with a mass between 8 and 20 times that of the Sun exhausts its nuclear fuel, it collapses under its own gravity. The core compresses to an incredibly dense state, forming a neutron star. These stars are incredibly dense, with a mass about 1.4 times that of the Sun but a radius of only about 10 kilometers. 2. Binary neutron star systems. In some cases, two neutron stars can form in a binary system. This happens when both stars in a binary system undergo supernova explosions, leaving behind two neutron stars. These neutron stars orbit each other, gradually losing energy through the emission of gravitational waves, which are ripples in spacetime predicted by Einstein's theory of general relativity. 3. Spiral inward and collision. As the neutron stars lose energy, they spiral closer together. This process can take millions to billions of years. When they get close enough, the gravitational forces become extremely strong, causing them to accelerate towards each other. The final moments before the collision are incredibly violent, with the stars moving at a significant fraction of the speed of light. For gravitational waves, the inspiral and collision of neutron stars produce gravitational waves, which are detected by observatories like LIGO and Virgo. The first direct detection of such an event, known as GW 170817, occurred in 20171. This event confirmed that neutron star mergers are a source of gravitational waves and provided a wealth of information about these phenomena. 5. The collision. When the neutron stars collide, the impact is cataclysmic. The collision can result in the formation of a more massive neutron star or, if the combined mass exceeds a certain limit, the Tolman-Oppenheimer-Volkoff limit, a black hole. The collision releases an enormous amount of energy, equivalent to the energy output of all the stars in the observable universe for a brief moment. 6. Electromagnetic radiation and kilinovae. The collision also produces a burst of electromagnetic radiation, including gamma rays, X-rays, and visible light. This burst is known as a kilonova. Kilonovae are powered by the radioactive decay of heavy elements formed during the merger. The event GW 170817 was accompanied by a kilonova, providing direct evidence that neutron star mergers produce heavy elements like gold and platinum-2. 7. Heavy element formation. One of the most significant outcomes of neutron star collisions is the creation of heavy elements through a process known as rapid neutron capture, or the R process. During the collision, the environment is so neutron-rich that it allows for the formation of elements heavier than iron, such as gold, platinum, and uranium. These elements are then scattered into space, contributing to the cosmic abundance of heavy elements too. 8. Implications for astrophysics and cosmology. Neutron star collisions have profound implications for our understanding of the universe. They provide insights into the behavior of matter at extreme densities, the nature of gravitational waves, and the origins of heavy elements. Observations of these events also help refine our models of stellar evolution and the dynamics of binary systems. Summary. In summary, neutron star collisions are extraordinary events that play a crucial role in the cosmos. They produce gravitational waves, electromagnetic radiation, and heavy elements, offering a unique window into the most extreme conditions in the universe. The study of these collisions continues to advance our knowledge of fundamental physics and the workings of the universe. A kilonova, also known as a macronova, is a transient astronomical event that results from the merger of two neutron stars or a neutron star and a black hole. The term kilonova reflects the fact that these events are about 1,000 times brighter than a typical nova, but not as bright as a supernova. 2. The merger process. When two neutron stars in a binary system spiral inward and collide, they create a kilonova. This process begins with the emission of gravitational waves, which cause the neutron stars to lose energy and move closer together. As they approach each other, tidal forces distort the stars, and the intense gravitational interaction leads to their eventual merger. 3. Gravitational waves. The inspiral and collision of neutron stars produce gravitational waves, which are ripples in spacetime. These waves were first directly detected by the LIGO and Virgo observatories in 2017 during the event GW 170817. The detection of gravitational waves from neutron star mergers provides crucial information about the masses and dynamics of the merging objects. 4. Electromagnetic radiation. The collision of neutron stars releases a burst of electromagnetic radiation across the spectrum, including gamma rays, X-rays, ultraviolet, optical, infrared, and radio waves. This radiation is produced by the radioactive decay of heavy elements formed during the merger. The initial burst of gamma rays is followed by a longer-lasting afterglow in other wavelengths. 5. Heavy element formation. One of the most significant outcomes of a kilonova is the creation of heavy elements through the rapid neutron capture process, or R process. During the merger, the environment is extremely neutron-rich, allowing for the formation of elements heavier than iron, such as gold, platinum, and uranium. These elements are synthesized in the debris ejected from the collision and are later dispersed into space. 6. Optical and infrared emission. The optical and infrared emission from a kilonova is powered by the radioactive decay of newly formed heavy elements. This emission can be observed as a brightening and fading light curve over days to weeks. The color of the light changes from blue to red as the ejector expands and cools. Observations of kilonovae in these wavelengths provide insights into the composition and amount of ejected material. 7. Kilonovae and gamma-ray bursts. Kilonovae are often associated with short gamma-ray bursts, GRBs. These bursts are thought to be produced by the relativistic jets launched during the merger. The detection of a kilonova following a short GRB provides strong evidence for the connection between these two phenomena. The event GW170817 was accompanied by a short GRB, confirming this association. 8. Observational significance. The observation of kilonovae is crucial for several reasons. Astrophysics. They provide a unique laboratory for studying the physics of extreme environments, such as the behavior of matter at nuclear densities and the mechanisms of heavy element formation. Cosmology. Kilonovae can be used as standard candles to measure cosmic distances and the expansion rate of the universe. Multi-messenger astronomy. The simultaneous detection of gravitational waves and electromagnetic radiation from kilonovae allows for a more comprehensive understanding of these events. 9. Recent discoveries. The first confirmed observation of a kilonova was associated with the gravitational wave event GW170817. This discovery marked a significant milestone in astronomy, as it was the first time that both gravitational waves and electromagnetic radiation were detected from the same event. Since then, several other kilonovae have been observed, furthering our understanding of these phenomena. Summary. In summary, kilonovae are extraordinary events resulting from the merger of neutron stars or neutron stars and black holes. They produce gravitational waves, electromagnetic radiation, and heavy elements, offering valuable insights into the most extreme conditions in the universe. The study of kilonovae continues to advance our knowledge of astrophysics, cosmology, and the origins of heavy elements. The R process, rapid neutron capture process. The primary mechanism for the formation of heavy elements in neutron star collisions is the rapid neutron capture process, or R process. This process occurs in environments with a high density of free neutrons, which are abundant during the merger of neutron stars. 2. Neutron star composition. Neutron stars are incredibly dense objects composed mostly of neutrons. When two neutron stars collide, they release a vast amount of neutron-rich material into space. This material is ejected at high velocities, creating the perfect conditions for the R process to occur. 3. Conditions for the R process. For the R process to take place, several conditions must be met. High neutron density. The environment must have a high density of free neutrons. Neutron star collisions provide this in abundance. High temperature. The temperatures during the collision are extremely high, which helps to overcome the energy barriers for nuclear reactions. Rapid time scale. The process occurs on a very short time scale, allowing nuclei to capture multiple neutrons before they can decay. For nucleosynthesis during the collision. During the collision, the neutron-rich material is ejected and undergoes rapid neutron capture. Here's how it happens. Neutron capture. Atomic nuclei in the ejected material capture free neutrons rapidly. This increases the atomic mass of the nuclei. Beta decay. Some of the newly formed nuclei are unstable and undergo beta decay, where a neutron is converted into a proton, emitting an electron and an antineutrino. This process changes the element to a higher atomic number. Formation of heavy elements. Through successive neutron captures and beta decays, elements heavier than iron, such as gold, platinum, and uranium, are formed. 5. Observational evidence. The first direct evidence of heavy element formation in neutron star collisions came from the observation of the kilonova associated with the gravitational wave event GW170817. The light from this kilonova showed spectral lines corresponding to heavy elements, confirming that such mergers are a significant source of these elements. 6. Contribution to the cosmic abundance of heavy elements. Neutron star collisions are now understood to be a major source of heavy elements in the universe. Studies suggest that these events have produced more heavy elements in the last 2.5 billion years than mergers between neutron stars and black holes too. This has profound implications for our understanding of the chemical evolution of galaxies and the origin of elements found on Earth. 7. The role of supernovae. While supernovae also contribute to the formation of heavy elements, they are not as efficient as neutron star collisions. Supernovae primarily produce elements up to iron through fusion processes, but the R process in supernovae is less prolific compared to neutron star mergers too. Summary. In summary, the collision of neutron stars creates the ideal conditions for the rapid neutron capture process, leading to the formation of heavy elements. These collisions eject neutron-rich material, which undergoes rapid neutron capture and beta decay, forming elements like gold and platinum. Observations of kilonovae provide direct evidence of this process, highlighting the significant role of neutron star mergers in the cosmic production of heavy elements. One of the primary sources of energy in a neutron star collision is the emission of gravitational waves. As the neutron stars spiral towards each other, they lose energy in the form of gravitational waves. These waves carry away a significant amount of energy, causing the stars to move closer together. The energy emitted in gravitational waves during the final moment of the merger can be equivalent to the mass energy of several solar masses. 2. Kinetic energy. As the neutron stars approach each other, their orbital velocities increase dramatically. Just before the collision, they can reach speeds of up to 30% of the speed of light. The kinetic energy associated with these high velocities is immense. When the stars collide, this kinetic energy is converted into other forms of energy, including heat and radiation. 3. Electromagnetic radiation. The collision of neutron stars produces a burst of electromagnetic radiation across the spectrum, from gamma rays to radio waves. This burst is known as a kilonova. The initial gamma ray burst, GRB, is extremely energetic, releasing more energy in a few seconds than the Sun will emit over its entire 10-billion-year lifetime. Following the GRB, the kilonova emits light in other wavelengths, powered by the radioactive decay of heavy elements formed during the merger. 4. Thermal energy. The collision generates extreme temperatures, reaching billions of degrees Kelvin. This thermal energy contributes to the emission of electromagnetic radiation and drives the synthesis of heavy elements through the rapid neutron capture process, R process. The heat also causes the ejected material to glow brightly, contributing to the kilonova's light curve. 5. Heavy element formation. The energy released during the collision facilitates the formation of heavy elements. The R process requires a high-energy environment with abundant neutrons. The collision provides these conditions, allowing for the creation of elements heavier than iron, such as gold, platinum, and uranium. The energy involved in these nuclear reactions is substantial, adding to the overall energy budget of the event. 6. Black hole formation. In some cases, the merger of neutron stars results in the formation of a black hole. If the combined mass of the neutron stars exceeds the Tolman-Oppenheimer-Volkoff limit, the remnant collapses into a black hole. The formation of a black hole releases a tremendous amount of energy, as the remaining matter is rapidly accreted onto the black hole, emitting intense radiation and possibly launching relativistic jets. 7. Energy comparison. To put the energy of a neutron star collision into perspective, consider that the total energy released can be on the order of 10^53 ergs. This is roughly equivalent to the energy output of all the stars in the observable universe over a few seconds. It's also comparable to the energy released in a supernova, but concentrated in a much shorter time frame and involving different physical processes. Summary. In summary, neutron star collisions are incredibly energetic events, releasing vast amounts of energy through gravitational waves, kinetic energy, electromagnetic radiation, thermal energy, and nuclear reactions. These collisions not only provide a spectacular display of energy but also play a crucial role in the synthesis of heavy elements and the dynamics of the universe. Formation of a more massive neutron star. If the combined mass of the merging neutron stars is below a certain threshold, the Tolman-Oppenheimer-Volkoff limit, approximately 2 to 3 times the mass of the Sun, the result can be a more massive neutron star. This newly formed neutron star may be stable or temporarily stable, eventually collapsing into a black hole if it exceeds the mass limit. 2. Formation of a black hole. If the combined mass exceeds the Tolman-Oppenheimer-Volkoff limit, the remnant will collapse into a black hole. This process is extremely energetic and can result in the emission of intense radiation and the formation of relativistic jets, which are associated with short gamma-ray bursts, GRBs. 3. Ejection of material. During the collision, a significant amount of neutron-rich material is ejected into space. This ejected material undergoes rapid neutron capture, R process, nucleosynthesis, forming heavy elements like gold and platinum. The ejected material contributes to the kilonova, a bright transient event observable in multiple wavelengths. 4. Electromagnetic afterglow. Following the initial burst of gamma rays, the collision produces an afterglow of electromagnetic radiation across the spectrum. This afterglow can last 4 days to weeks and provides valuable information about the dynamics of the merger and the properties of the ejected material. 5. Gravitational waves. The collision generates gravitational waves, which are ripples in space-time. These waves carry away energy and angular momentum from the system. The detection of gravitational waves from neutron-star mergers provides insights into the masses and dynamics of the merging objects. Summary. In summary, the aftermath of a neutron-star collision can result in the formation of a more massive neutron star or black hole, the ejection of neutron-rich material, the production of heavy elements, and the emission of electromagnetic radiation and gravitational waves. Each of these outcomes contributes to our understanding of the universe and the processes that govern it. The detection of gravitational waves from neutron-star mergers has provided valuable data on their frequency. The first confirmed detection of a neutron-star merger, GW170817, occurred in 20,171. Since then, several other mergers have been detected by observatories like LIGO and Virgo, helping to estimate the rate of these events. 2. Estimated frequency. Based on current observations and models, the estimated frequency of neutron-star mergers in a galaxy like the Milky Way is about one event every 10,000 to 100,000 years. However, when considering the entire observable universe, these events are much more frequent. It's estimated that neutron-star mergers occur roughly once per month across the universe. 2. 3. Factors influencing frequency. Several factors influence the frequency of neutron-star colisions. Binary star systems. The formation of binary neutron star systems is a prerequisite for these colisions. The initial conditions of star formation and the evolution of binary systems play a crucial role. Stellar evolution. The life cycles of massive stars, including supernova explosions, determine the creation of neutron stars. Gravitational wave emission. The loss of energy through gravitational waves causes neutron stars in a binary system to spiral inward and eventually merge. The timescale for this process can vary widely, from millions to billions of years. 4. Observational challenges. Detecting neutron star mergers is challenging due to their transient nature and the vast distances involved. Gravitational wave observatories have significantly improved our ability to detect these events, but the sensitivity and coverage of these detectors are still limited. As technology advances, we expect to detect more mergers and refine our estimates of their frequency. 5. Implications for astrophysics. Understanding the frequency of neutron-star mergers has several important implications. Heavy element formation. These colisions are a primary source of heavy elements in the universe, such as gold and platinum. Knowing their frequency helps us understand the abundance of these elements. Cosmic evolution. The rate of neutron-star mergers provides insights into the evolution of binary star systems and the dynamics of galaxies. Gravitational wave astronomy. Frequent detections of neutron-star mergers enhance our understanding of gravitational waves and improve our ability to use them as tools for exploring the universe. Summary. In summary, neutron-star colisions are relatively rare events in individual galaxies but occur more frequently across the entire universe. Advances in gravitational wave astronomy have improved our ability to detect these events and estimate their frequency. Understanding the rate of neutron-star mergers is crucial for studying heavy element formation, cosmic evolution, and the nature of gravitational waves. Formation of massive binary stars. The process begins in dense molecular clouds, also known as stellar nurseries, where regions of higher density collapse under their own gravity to form stars. If two stars form close to each other, they can become gravitationally bound, creating a binary star system. 1. 2. Evolution of massive stars. For a binary neutron star system to form, both stars in the binary system must be massive enough, typically 8 to 20 times the mass of the Sun, to end their lives as neutron stars. These massive stars evolve through several stages. Main sequence. Both stars burn hydrogen in their cores. Red giant / supergiant phase. The stars exhaust their hydrogen and start burning heavier elements, expanding into red giants or supergiants. Supernova explosion. Each star eventually undergoes a core collapse supernova, leaving behind a neutron star. 3. Supernova and neutron star formation. When the first star in the binary system explodes as a supernova, it leaves behind a neutron star. The explosion can impart a kick to the neutron star, potentially altering the orbit of the binary system. If the system remains bound, the second star will eventually undergo a similar process, resulting in a second neutron star too. 4. Common envelope phase. During their evolution, the stars may go through a common envelope phase. This occurs when one star expands and engulfs its companion, leading to a shared outer envelope. The friction within this envelope causes the stars to spiral closer together, losing angular momentum and energy. This phase is crucial for bringing the stars close enough to eventually merge. 3. 5. A gravitational wave emission. Once both stars have become neutron stars, they continue to orbit each other, gradually losing energy through the emission of gravitational waves. This process causes the orbit to shrink over time, bringing the neutron stars closer together. The timescale for this in-spiral can range from millions to billions of years. 4. 6. Final merger. Eventually, the neutron stars spiral inward to the point where they collide and merge. This merger produces a burst of gravitational waves and electromagnetic radiation, and can result in the formation of a more massive neutron star or a black hole, depending on the total mass of the system. Summary. In summary, binary neutron star systems form from massive binary stars that evolve through supernova explosions to become neutron stars. The system may undergo a common envelope phase, and the neutron stars gradually spiral inward due to gravitational wave emission, eventually merging. This process is complex and involves multiple stages of stellar evolution and interaction. Neutron star binaries can be observed through various forms of electromagnetic radiation, including radio waves, X-rays, and visible light. Radio waves, pulsars, which are rotating neutron stars emitting beams of radio waves, can be detected using radio telescopes. When a pulsar is part of a binary system, its regular pulses can be used to infer the presence of a companion neutron star. The timing of these pulses can reveal details about the orbit and masses of the stars. X-rays. Neutron star binaries can also emit X-rays, especially if one of the stars is accreting matter from its companion. This accretion process heats the material to very high temperatures, producing X-rays that can be detected by space-based observatories like the Chandra X-ray Observatory and XMM Newton. Visible light. In some cases, the companion star in a neutron star binary can be a normal star, which can be observed in visible light. The motion of this star can provide information about the neutron star's presence and properties. 2. Gravitational wave observations. The most direct method of observing neutron star binaries is through the detection of gravitational waves. These ripples in spacetime are produced by the in-spiral and merger of neutron stars. Observatories like LIGO and Virgo have detected several such events, providing detailed information about the masses and dynamics of the merging stars. 3. Multi-messenger astronomy. The combination of electromagnetic and gravitational wave observations, known as multi-messenger astronomy, provides a comprehensive view of neutron star binaries. For example, the event GW170817 was observed both through gravitational waves and electromagnetic radiation, offering unprecedented insights into the merger process and its aftermath. 4. Pulsar timing. Pulsar timing is a precise method used to study neutron star binaries. By measuring the arrival times of pulses from a pulsar, astronomers can detect variations caused by the gravitational influence of a companion neutron star. This technique allows for the measurement of orbital parameters and the masses of the stars with high precision. Summary. In summary, we can observe neutron star binaries directly through electromagnetic radiation, radio waves, X-rays, and visible light, gravitational waves, and pulsar timing. These observations provide valuable information about the properties and dynamics of these fascinating systems. Detection of gravitational waves. The Laser Interferometer Gravitational Wave Observatory (LIGO) and the Virgo detector first detected the gravitational waves from GW170817. These waves were produced by the in-spiral and merger of two neutron stars. The signal lasted for about 100 seconds, which is much longer than the signals from black hole mergers, indicating the smaller masses of neutron stars. 1. 2. Gamma ray burst. Approximately 1.7 seconds after the gravitational waves were detected, NASA's Fermi Gamma Ray Space Telescope observed a short gamma ray burst, GRB, from the same region of the sky too. This was the first time that both gravitational waves and gamma rays were detected from the same astronomical event, confirming the connection between neutron star mergers and short GRBs. 3. Multi-messenger observations. Following the initial detect ions, a global network of observatories quickly mobilized to observe the event across the electromagnetic spectrum. Within hours, telescopes detected the optical counterpart of the merger in the galaxy NGC 4993, located about 130 million light-years away. 3. This optical counterpart, known as a kilonova, was observed in visible, ultraviolet, infrared, and radio wavelengths over the following days and weeks. For heavy element formation, spectroscopic observations of the kilonova revealed the presence of heavy elements, such as gold and platinum, formed through the rapid neutron capture process (R process). This provided direct evidence that neutron star mergers are a significant source of heavy elements in the universe. 5. Implications for astrophysics. The observation of GW 170817 had profound implications for several areas of astrophysics. Gravitational wave astronomy. It confirmed that neutron star mergers produce detectable gravitational waves, opening a new era of multi-messenger astronomy. Gamma ray bursts. It established the link between short GRBs and neutron star mergers. Cosmology. The event allowed for an independent measurement of the Hubble constant, which describes the rate of expansion of the universe. Nucleosynthesis. It provided direct evidence for the production of heavy elements in neutron star mergers. Summary. In summary, the first observation of a neutron star collision, GW 170817, was a groundbreaking event that combined gravitational wave and electromagnetic observations. It confirmed theoretical predictions about neutron star mergers, provided insights into the production of heavy elements, and demonstrated the power of multi-messenger astronomy. That was all. Goodbye.